Okay, off we go. So I'm sure you noticed Canvas is down, and so we can't do the attendance quiz. I have no reasonable alternatives, so oh well. There just isn't going to be an attendance quiz today. Okay, sorry about that. So here's where we were last time. We were talking about change of variables. Very valuable idea in integration. So in particular, when you have an integral to compute, if that integral is done over some domain that's undesirable for whatever reason, and usually a matter of there being weird shape and corners in the slicing process, maybe the edges have equations that are hard to work with, will mess up your bounds and therefore your outer integrand, and just it's going to be tough going. The big trick, if you can, some way or another, if you can view that domain as being the image of something nicer. That's the big idea. If you can view your ugly domain as being the image by way of some function of something nicer, then the pullback process, right, the process of basically plugging in, will produce a new integral defined on your pullback domain that, again, by our premise, a nicer, more desirable domain. And the only thing you really need to make this work, aside from, you do have to identify what is the change of variables function and what is your pullback domain. The only thing you have to remember beyond that is don't forget your stretching factor. And we have our formula here for how to compute the stretching factor. Don't forget there's also this, I think, highly desirable, convenient, let's say it this way, highly convenient notation, for that stretching factor. Just make sure to stick that stretching factor in there and you're good to go. Okay, so we did an example last time, and in this example, let me confess, I did kind of manufacture this example where I just gave you the change of variables function. That won't always be the case, right? And then likewise, I gave you the pullback domain. And that won't always be the case. Okay. All right. So there are some kinds of transformations that can be particularly useful. And here's a couple of examples. For example, the translation function. So what this does is this takes any point in the UV plane and will add the vector a comma b. Right, so that's actually a pretty useful change of variables function. And now if you think about it, then when you pull back through that process, effectively starting from your original domain and looking back to the new pullback domain, it'll kind of translate backwards. Right? So you do have to keep in mind that, because pullbacks are sort of a, going backwards kind of a thing, there is a sort of an oppositeness in how these work. And so likewise, if you have a stretching transformation, then that'll effectively squish your domain. And if you rotate counterclockwise, that'll cause your domain to rotate clockwise, etc. So I'm going to show you an example of the latter. This example here. Now, notice we start off with an integral. Integral is defined on a square with certain vertices given, and that's this square, like so. And let's just for the real quick moment, let's entertain doing this the old-fashioned way, depending on how you slice. Right, one way or the other, though, you're going to slice through two corners. Right, so this is 3 iterated integrals. Doable but undesirable. All else being equal, we'd prefer to avoid that. And side note, in doing those 3 iterated integrals, I'd have to find the equations of these 4 edge lines, and so there'd be a little bit of it's not hard, but it's just tedium, it's an effort. Okay. So here's the big idea. What I would like to be able to do, if I could, I would like to be able to take this square and kind of tilt it to the right. If I were to tilt it to the right, then it would be like I have drawn over there, like I have drawn here. It would be, one vertex at the origin, parallel to the axes. This is a great domain. Love this domain. The way I'm going to accomplish that is I'm going to view this as it is as being the result of rotating counterclockwise. All right, remember, that is the deal, right? If you want to do a change of variables, the idea is we have to view our undesirable domain as being the image of the more desirable domain. And so by what sort of a rotation can I view this given undesirable blue given domain as being the image of what I would rather deal with, and that is by a counterclockwise rotation. Okay. So then when I say pull back, my new domain, the thing that I rotate counterclockwise to produce my ugly blue domain, the thing that I rotate counterclockwise is that green thing. In other words, it's the thing that I wanted to pull back into. Everybody see that? Everybody happy? Okay, so details follow. So first of all, let's talk about this change of variables function, this rotation. Let me just clean up my mess. Actually, that's kind of okay. So this, I'll go ahead and do that. So this counterclockwise rotation, by the way, you can do a little bit of trig. Based on where this point is, and persuade yourself that the angle by which we're rotating is pi over 6. That's just a little bit of trig and geometry, so make sure you're good to go with that. So the question then is, how do I accomplish a counterclockwise rotation by angle pi over 6 and linear algebra? Right, so we talked about that long ago. It's a linear algebra thing, and short version, the columns are the images of the standard basis vectors, all that. Okay, so make sure that you can persuade yourself that this change of variables function is going to be that right there. Okay, so it's all over with the shouting at this point. We know what our pullback domain is going to be. Our pullback domain is 0 to 2, 0 to 2, right? Nice and easy. Now I do have to compute the stretching factor. All right, so I'm going to have to compute the various partials and blah, 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 and the stretching factor very nicely. Just 1. By the way, real quick, of course it is. I mean, let's think about what we're actually doing here. We are, in fact, just rotating, right? And when you rotate things, they don't change in size, right? So plausible, right? Everybody believe it? Seems reasonable. Okay. That said, even though it's what I'm going to call geometrically expected, you do have to show the calculation. But anyway. Okay, so let's proceed. Our stretching factor. Don't forget to stick that in there. Don't forget your absolute values. Now, obviously, multiplying by 1 doesn't do anything. Obviously, taking the absolute value of something that's already positive doesn't do anything. But by writing this down, I'm showing 2 things. First of all, I'm showing that I knew that there were supposed to be absolute values there. Your grader will appreciate that. And I'm showing that I did not, in fact, forget to put my stretching factor in there. Right? Of course, I knew to put it in there. You can see I actually did it. Right? So that removes that doubt in the grader's mind as well. So keep in mind, a happy grader is a generous grader. Right? So little things like that are prudent. Let's see here. We have to plug in our integrand 2x minus y. I got to see how does that become this. And, well, what do I do with this x? How do I know where x comes from? Keep in mind, x is one of the outputs. It's the first output from our linear transformation. And we have the formula for it right here. X is that dot product. Remember, the change of variables function explicitly tells you how to do the pullback because you're just plugging in from the change of variables function. Likewise for y. Is that cool? Everybody with me? Okay, so much easier integral results. Right, so we get to do this integral instead of that integral. Now, at a casual, careless glance, the one on the left looks nicer because, well, I mean, the constants are slightly prettier constants. But this is a micro point, right? I mean, these are still constants, whatever, right? The actual integration, finding antiderivatives here, is pretty straightforward. The advantage of the green one, though, is we have totally awesome bounds. That's a single iterated integral. And remember, if we did it with the blue integral, we would have terrible bounds. We would have 3 separate iterated integrals, non-constant bounds, and it'd just be much harder, much more work. Everybody with me? All right. Okay, a couple of quickies, just for regularity reasons. This is math major stuff that we don't need to worry about. We do need the change of variables function to be continuously differentiable and invertible. If it's not invertible, then you have to worry about double counting, and we want to make sure we don't do that. Okay. Good news, that's rarely going to be an issue. It's something that's going to be pretty straightforward, so nothing to worry about. Okay, so nice observation here. Let me remind you that if you have a change of variables function that gives x and y as functions of u and v, here's our stretching factor formula, old news. Let me be a little bit more specific here. You don't want to memorize these formulas in terms of letters of the alphabet, right? Obviously. So why is it x and y, and why is it u and v, and how will you keep that straight? And the answer is, you're always going to take the partials of the output variables with respect to the input variables. So that's a good way to think of it. It's always consistently, no matter what the letters are called, no matter which direction the arrow goes, it's always the partials of the outputs with respect to the inputs. Okay, now that noted, let's imagine what would we do if we wanted to talk about the inverse transformation. I wanted to go backwards. What's the stretching factor for this opposite direction, this kind of dark blue transformation? Well, it's going to be the partials of the outputs. Right, let's get rid of that. The function goes to the left. The outputs are now u and v. We're going to take the partials with respect to the inputs. I'll do it like this. X and y. Is that cool? Everybody with me? Alrighty. Well, now let's imagine that I have some little piece of area here. And what would happen if I look at its image over there, and then whatever that image is, come back to the UV plane with it? And, well, of course, this being the inverse of that, the answer is nothing happens. Right? But I can also say this a different way. I can say, well, when I do the purple path, I'm multiplying by that factor. And then when I do the dark blue path on the way back, I'm multiplying by another subsequent factor. And altogether, again, as we observed, altogether, nothing happened. Altogether, I'm back to the same area I had. Altogether, I've multiplied by a combined factor that has to be 1. So we get this nice little result here that these two stretching factors multiply to 1, or said differently, these two stretching factors are reciprocals of each other. And this is another reason that I like this notation. Right? It's a little sketchy notation because I'm writing it as if it's a fraction, and it's definitely not a fraction. It's a determinant, not a fraction. But in this way, too, it behaves like a fraction, and that can be extremely handy. Okay, so nice little punchline. We're going to make use of that in this next example. This next example is a little bit of a tricky one. Very clever idea here. So here we go. We have 4 curves. And those 4 curves bound this dark gray region that I have shaded there. And for whatever reason, let's suppose we want to do an integral on this region. That makes sense? Everybody see what I want to do? By the way, let me address something you may be thinking. You may be thinking, that's, oh my God, so weird. How manufactured, how arbitrary, how irrelevant. What's the real world got to do with this? And I'll tell you where I got this example from. Something very, very, very similar to it. Slightly different numbers, kind of, keep things relatively simple. But this basically comes straight out of a thermodynamics class that I took when I was in college. And when you do thermodynamics, there are 4 curves that look a lot like these. The only difference is this exponent that's a 2 here is not a 2. It's a little bit different number. But anyway, basically this example, except for micro details, and a calculation of an integral on a domain like this is relevant to seeing how this thing called the Carnot cycle works. And if any of y'all have ever had a thermo class, you've heard of the Carnot cycle and Carnot engine. A very important construction in thermodynamics. So pretty natural, as it turns out. Anyway, how are we going to do this integral? Here's the trick, and just follow the trick. It's very clever. It's very particular. If 2 of your curves are level sets of a particular function, right? Notice these first 2 curves are level sets of the same function, xy. And if the other 2 of your curves are level sets of another particular function, same function, in this case xy squared. So that's what we've got, right? We've got 4 level sets that pair up as 2 level sets each of 2 functions. The slick move is to let u be the first function, let v be the second function, and I claim that awesome ensues. Right? So let's see how this works out super nicely. So let's look at let's look at this curve, xy equals 1. That's a weird curve, undesirable, but recall I just set u equal to xy. Okay, well, wait a second. If u is xy, and if xy is 1, that means u equals 1. And that means that this undesirable edge turns into a straight line in the UV plane. What do you think? Everybody see that? Likewise for the other 3. So this little move, and it's a slick move, and you got to do it just so, right? But you set up your change of variables function like this, and again, now we have an opportunity to change the variables. Undesirable domain, totally awesome domain. Details ensue. Okay, so let's talk about some of those details. Here's an ugly little detail, and that is that the function's going the wrong way. Right, a little minor point, right? I want the function to be going that way so I can pull back to this domain that I want. The function is, it's like, why would I want to pull back this way? It's just going the wrong way. All right, so that's not good. But this is invertible, and there is a function that's going that way, and I can say, well, let's pull back through, turn this around, however that would work. But this is the function I want to pull back through. Now, side note, the formula for this function, I could totally solve. I could totally solve for x and y as functions of u and v. I don't want to. It's not that it's hard, even, right? But keep in mind, the purpose of this example is to illustrate the method, right? And so I'm going to say, let's presume that for whatever reason we don't want to solve for x and y here. By the way, I could totally have constructed an example where you can't solve for x and y, but then the algebra would have been weirder, and I think that would have been counterproductive. Okay, so we're not going to solve for x and y, just to show we don't have to. Okay, now I'm going to real quick skip the next couple of lines. I'm going to come down to here, then we'll go back up in just a second. Recall, this is the integral that I want to compute. It's defined on this ugly domain that I don't like. I would like to pull that back, turn that into an integral on the rectangle that we just talked about, that I do like. And I know that the integrand is whatever it is, and that's going to come along for the ride. And I know also, let's see here, I'll do it like this. This dx dy, I'm going to want it to rewrite like this. Let me get rid of the distractions here. Right, I know that my dx dy is going to be some stretching factor times du dv, and let's just think through for a second. What is this? What should this stretching factor be, and how do I know that it's the one that I wrote down here? I mean, there are arrows going two different directions. Why wouldn't this be du, partial uv with respect to partial xy? I mean, how do I know? And the answer, and this is a cheap trick, but it's reliable and convenient. The answer is, well, I need those to cancel, right? Now, again, that's garbage. There is no cancellation, but this nonsense will always lead you the right direction. So I strongly encourage this. I think it's very helpful, right? Decide which of these, do I want partial xy, partial uv, or do I want partial uv, partial xy? Decide by put there which one will make the faux cancellation work the way it's supposed to. Is that cool? Okay, so I need partial xy, partial uv. I don't have formulas for x and y, but I do have formulas for u and v, and I can compute partial uv, partial xy. That's just a couple of easy partial derivatives, nothing to it. Let's see if I can fit this all. Yeah, close enough. So I have partial uv, partial xy. I need partial xy, partial uv, so I can compute the thing that I need as the reciprocal of this thing that I have. Is everybody happy? Okay. Cool. And then it's kind of all over with the shouting. You do have to, multiply these out, and then you get your integrand. And again, quick careless glance, this kind of looks like an integral that we could totally compute. The domain is a rectangle, constant bounds, seems easy. Okay, let's take a more careful look. This is a UV integral. The integrand is not written in terms of u's and v's. That's going to happen when you do things backwards, like I'm doing them here. That's what you're going to end up with. So we do have to, in some sense, face the music. I didn't want to have to solve for x and y in terms of u and v. tempting to say that I will, but in fact I still won't. I don't have to solve for x and y individually. I only need to solve for the actual integrand that I'm going to have to deal with. So I don't have to solve for two separate things. I only have to solve for one of them. Is that cool? Everybody see why we're doing that? Okay, now how this works is, I'm sorry to say, non-algorithmic, and it's going to be a little bit different every time, and you have to make reasonable guesses. There is, in fact, a certain amount of guesswork that happens in these examples. So I'm going to try to motivate what I'm doing in this example, and you're going to try to find similar motivations in examples that you'll do. All right, here's what we've got. My integrand is a product of powers of x and y. I need to write that in terms of u and v. Wait a minute, u and v are products of powers of x and y. Okay, so what that means is I want to write this product of powers of x and y in terms of these two other products of powers, products of powers of x and y. Now, here's where I'm going to speculate, and this is a guess. Right? I'm going to take a guess as to what the form of the answer might be. This is a wild guess. Seems reasonable, though. If I have products of powers, and if I take a product of powers of those products of powers, I think I'm going to get a product of powers. Right? Now that's an algebraic appeal. Right? Doesn't that seem reasonable? If I have in blue here products of powers, and then I take a product of powers of those products of powers, I'm going to get a product of powers, and the hope is that I can choose the A and the B so that I can make the resulting product of powers the thing that I actually need. Let's take a moment to sit on that for a second. Who's got a question as to, does that seem like a reasonable thing to speculate? Right. Notice, for example, I could have speculated, I think this would have been foolish, I could have speculated, hey, maybe this thing in green is a linear combination of u and v. But it just doesn't seem like that ought to work. Just algebraically, it seems like that would be going in the wrong direction. So this, I feel like I can sort of see that that's going to work. So that's what I mean, guessing the form, right? What I have in purple there, I'm guessing what I'm going to do to the blue expressions to create the green expression. And then it's just a matter of finding the details. So the way we're going to find the details, we're going to multiply this out. Then I'm going to notice that for this to equal to that, I would need for the x exponents to be equal, and I would need for the y exponents to be equal. And I can then just solve for A and B. Now, that's details, right? So you all make sure you can do this, right? This is a linear algebra, a little quickie linear algebra thing, but you solve for those details, and now we have our answer that those give me these exponents that allow me to view my integrand in terms of u and v. And then it's plug and chug. What do you think? Everybody all right with that? Okay. Okay, good deal. Well, let's let me give you a little bit of a discussion about where the stretching factor formula came from. So we've done several examples at this point. So the mechanics of change of variables, we've got some wins under our belt. Now let's make sure we have some reasonable sense for why this works. Where did the stretching factor formula come from? And here's, again, what a stretching factor is. A stretching factor is if I have a little piece of area in the pullback domain, the G function is going to turn that into a piece of area in the given domain. But of course it might stretch it out, right? Those areas might not be the same. So I want to find what is this factor? By what do I multiply by the green area to get the blue area? And I'm going to answer that question by computing that blue area. And that blue area is a parallelogram. And that's a parallelogram in the plane. And we know how to compute areas of parallelograms in the plane. I just need to understand these edge vectors. And so in particular, let's try to ask, where does this edge vector here come from? So the idea is to realize that that edge vector comes from this edge vector, for example. Right? So if this parallelogram comes from that rectangle, then you look at one of the edges here, that'll produce one of the edges here. Well, this edge on the left is easy to write down as a vector. It's in the E1 direction. Its magnitude is the width of that rectangle, du. And how do we turn input vectors into output vectors? That's what the derivative matrix does. Right? So the derivative matrix, dg, that is what you multiply by that input vector to get that output vector. Does that kind of seem reasonable? Likewise for the other edge, of course. Once we have that figured out, it's kind of all over. We want to compute the area of a parallelogram. Area of a parallelogram in 2 dimensions. Absolute value of a determinant. That's just chapter 1, Math219, what have you, formula for the area of a parallelogram. These formulas right here, so that is that first column of that matrix. Again, that's how you compute the area of a parallelogram. Likewise for the other one. And then y'all can do the resulting linear algebra. This is a good exercise. Make sure you're good with that linear algebra. Come ask me if you have any trouble, of course. Right? And notice what we end up with, exactly what we needed. That area comes from this area, which conveniently showed up right there, as being multiplied by that factor. That's our stretching factor. And that's the formula that I claimed several pages back. So that's how the calculation goes. I have left some details for you all to think through, of course, but big picture, that's the big idea, and that's why it works. Everybody okay? Everybody doing all right? Okay, let's talk about 3-dimensional change of variables. Good news, it's exactly the same. Practically identical. Certainly the same in the big picture. If you have some integral that's defined on an that's defined on an ugly domain like this, which I claim would be a nightmare of a domain. Keep in mind, as you're slicing up your domain, every time you hit a corner, you got to start with a whole new iterated integral. There's a lot of corners there, right? Furthermore, each slice that I take has a lot of corners. Right? So these can get out of hand fast. You might be looking at something like this. You might end up with 20 or 30 iterated integrals. Not reasonable to have to try to do it that way, right? Not at all. So the big idea, again, is if you can view that as being an image, in particular, hopefully an image of something nicer, right? Then the pullback allows you to instead compute a different integral over this much more desirable pullback domain, and again, life is good. Again, the big asterisk in order to make this work is you just need to know what the stretching factor is, right? So how much do volumes get stretched? It's the seemingly exact same formula. It's the absolute value of the Jacobian determinant. It's a 3x3 a 3x3 derivative matrix instead of 2x2. The shorthand is therefore 3 outputs with respect to 3 inputs, so slightly different looking notation, but totally analogous, right? It's morally it's the exact same thing. So great news there. And by the way, I mean, not that you would ever do this, but if you have to ever do a change of variables in a higher dimension, it's the same. Okay. So, now, real quick, a little preliminary note, cool fact about linear transformations. If you take the derivative matrix of a linear transformation, you get the exact same matrix. Isn't that weird? Sort of surprising. This is easy to check. Everybody should do this on your own time. It's easy to do. All you're going to do, let me tell you exactly how to do this. You're just going to pick a arbitrary matrix A, like A, B, C, D. Multiply by the x vector to get your coordinate formula for your linear transformation. Compute the derivative matrix of that. And then notice, sure enough, that derivative matrix is also ABCD. It's all there is to it. Real easy to check. Again, I strongly encourage everybody to give that a try. Come talk to me if you have trouble. So with that noted, let's go on to the example. This is a lovely example where we're going to turn a extremely difficult problem into an easy problem. Our domain here, we're looking at an integral. The domain for this integral is a parallelepiped, like I have drawn here. Edge vectors given. One corner at the origin. And let's just contemplate for a second what a nightmare this is. And at a quick glance, you think, oh, look at that. It's got flat faces. That's nice, right? Everything's kind of flat and straight. And it doesn't seem like it'd be that bad. This is a horrible nightmare of an example. Because it's got 8 vertices. And even if one's at the beginning and one's at the end, there's still 6 vertices in the middle. You should expect this to be 7 iterated intervals. And that's not even accounting for the fact that each one of the cross sections is itself not a rectangle, right? And each one of those cross sections is going to have corners and such. And so each one of those cross sections is going to be multiple iterated intervals. If I have not worked it out, and it depends on the particulars of the vector, but I think generically you would expect this to be at least 20 iterated intervals. So not reasonable, right? Completely impractical. Okay. So the big question, what should I use as my change of variables function? Right? So this parallelepiped is the image by what change of variables function of what pullback domain? And there's a wonderfully convenient answer to this question. It's almost like a little magic trick. These edge vectors, whatever are the edge vectors defining your parallelepiped, make those the columns of your matrix. Let's see, let me get okay. That matrix, use that to define a linear transformation. That's your change of variables function. That simple. Very cool little trick, right? And I'm claiming that this trick works, and I'll show you why in just a moment. But whatever the edge vectors are, make those the columns. Find the corresponding linear transformation. That's your change of variables function. Okay, now why does this work? This works because if you look one edge vector at a time, let's look at this E1 edge vector. Right, so where this new linear transformation we have, this new change of variables function, what does that do to E1? Right, E1 goes where over here? Well, E1, when you multiply by a matrix, first column, right? That's one of the basic rules of linear algebra is that the columns are the images of the standard basis vectors, right? So you multiply this matrix times E1. And, well, conveniently, when I say we get the first column, well, by construction, I've arranged for that first column to be my first edge of my parallelepiped. Right? And so the first edge of that cube goes to the first edge of this parallelepiped, and then analogously for all the other edges. Everybody buy it? So this is the trick. And it's kind of all over but the shouting at this point because, again, we started off interested in an integral defined on this nightmare of a domain. And we are now, after doing a pullback, right, change of variables pullback, I can say, well, instead, it's now an integral computed on everybody's favorite domain for a triple integral. Unit cube. World's easiest bounds. Single iterated integral. And all you got to do is remember to insert your stretching factor. So how are we going to compute that stretching factor? Well, that's pretty straightforward. I've got to compute the determinant of the Jacobian matrix. We've already shown that the Jacobian matrix is the matrix for the linear transformation. So I just have to compute the determinant of that little 3x3 matrix, and I can't do that in my head. Whatever that is, some number, right? So you insert that into your integral, and it's all over but the details. Yes?
If we were given t going the other way around, as in matrix A takes from the right side to the left side, would we then just use the transpose of A?
Well, I guess I don't quite understand the premise. So the point is, if this is the integral we're trying to compute, right? Let me get my colors straight. If this is the integral that I want to compute, and it's defined again on this domain, I don't really care what I'm given. I would construct that function going that way. You see what I'm saying? So I get to pick my change of variables function, and I'm going to pick it to go the direction that makes my life easy. So I would pick it like that. I'm not sure if I answered your question.
No, that makes sense.
Okay. Yeah, cool. Good. Anybody else?
The definition of where that formula for Z came from.
Oh, yeah. Good question. Okay, so he asks, so I wrote here that Z is this. So let's remember that Z, where is, okay, I will use blue. Z is the third output from the change of variables function. So it's the third vector in this list here. So X, Y, Z. Right? And so I'm looking for the third output. The third output that I get when I multiply A times UVW. So A times UVW, I would put UVW. And again, I want the third output. And so the third output would be the dot product with the third row, and that gives me that. Is that cool for everybody? Everybody see what I did there? Remember, the change of variables function always gives you the formulas for how to plug in. Z is the third output, so you look at your formula for your change of variables and you just straight up write down what that third output is. All right. Okay, so moving along. So we're done with what I'm going to call part 1 of section 5.5. Again, this is a monster section, so part 1 is kind of the generic change of variable stuff. Now I'm going to show you a collection of special case change of variables functions and examples, and they involve coordinate systems. And so this is going to be sort of part 2 here. There's some really cool ideas here. Y'all recall that polar coordinates you can think of as a function, right? We've written down these formulas previously, and you can view these as equations involving coordinates, but I like to think of them as making up a function. R and theta are the inputs, x and y are the outputs. Check it out. It's a change of variables function. Right? I can view R and theta as the pullback space, and x and y is maybe, sort of from where I would pull back into there. Because it's 2 variables in, 2 variables out. And if you use this as a change of variables function, you can compute your you can compute your Jacobian determinant, and you get R. Nice, simple little formula. Turns out, we're going to see a bunch of examples of this. This is one of the greatest change of variables functions you can choose. It's useful in just loads and loads of situations. Totally awesome. So don't think of this as an example per se. Think of this as like the example, right? This is so useful that we're not just going to use this Jacobian determinant here once. We're going to memorize this Jacobian determinant because we're going to be using this as a change of variables function just over and over and over and over again. Right? So make sure to remember that Jacobian determinant R. Now there is a sticky wicket on this. Don't forget that when you, let's see here, let me do it. I need, okay, that'll do. When we come to find the stretching factor is actually the absolute value of that Jacobian determinant, right? So I do need to figure out how to take the absolute value of that. Man, right? I hate having to have absolute values in my integrals because you got to break it up into cases, and it's just tedious. So here's the clever move. Slick idea. Clever move is just promise that you will only choose non-negative values of R. Right? If you promise, I will only use non-negative values of R. This is a personal choice. There's no law that says you have to do this. But this is a very clever personal choice. You make this one promise, R is now never negative, and now those absolute values, they just dissolve. It's like they were never there. Does that make sense? So, the really good idea, and here's the wonderful thing about it. I don't even like negative values of R. Right? The negative values of R are the confusing ones. So, I like to rephrase this as, if I promise to do only what I wanted to do anyway, then I also get to do the other thing I wanted to do, which is I kind of get rid of those absolute values. This is a win-win, right? So you just have to remember that even though it is win-win, it is nevertheless still, you got to be careful to make sure to actually live up to that promise. Okay. All right. Same thing for cylindrical. You can view it as a change of variables function. You can compute the stretching factor, the Jacobian determinant. You can promise to choose only non-negative values of R and make those absolute values go away. Practically the same thing. Spherical coordinates, practically the same thing. It's a function from 3 variables to 3 variables. You can choose to call that a change of variables function. Crazy useful. Comes up all the time. Probably the most, in 3 dimensions, the most common change of variables function is spherical coordinate change of variables function. You can compute its why do I keep saying that? You can compute its Jacobian determinant A little bit weird, a little bit different. It's not r, and it's not rho. It's rho squared sine phi. It's very different from what we got in polar and cylindrical. And by the way, another good reason to not fall for the over-interpreted claim that spherical is pretty much like polar. Very much not, right? Certainly for this calculation. So again, that's something that we have to take absolute values of. That's something that I have to figure out, okay, what promise can I make that will ensure that I don't need to worry about those absolute values? And, well, don't think about rho. Doesn't matter what you do to rho. Rho is going to get squared anyway. Rho could be positive, negative, zero, who cares, whatever. Rho is not the issue. The issue is I need to worry about this sine phi. And the way I make sine phi never be negative is I promise only to choose phi between 0 and pi. And again, those are the values I like anyway, right? 0 to pi, those are like the natural, kind of reasonable. All those other options, other values of phi are super weird and confusing. So again, do what you wanted to do anyway, and you also get to do the other thing you wanted to do, namely ignore the absolute values. Okay, we're out of time. We'll pick up here on Wednesday. Y'all enjoy the rest of your day. See you later.